Okay, guys, welcome. Today we're going to talk about graphs of functions. And specifically, we're going to talk about when we look at the graph of a function, you're essentially just looking at the graph um, of the related function, right? So if you have like f of x is equal to 3x plus 2, what we mean by the related function is you're just looking at the graph of 3x, y equals 3x plus 2, right? So that's just some terminology, but that's really what we're looking at. Okay, so in this first example, we're given an interesting example here. So we have that the commission earned by a door-to-door cosmetic salesperson is determined by this table, all right? So if the weekly sales is less than $300, we have that the commission is just 20% of sales, right? If the weekly sales is $300 or more, but less than 400, then we have that the commission is $60 plus 35% of the sales over 300, right? And then for 400 or more, we have that it's $95 plus 60% of sales over 400. Okay, so let's go ahead and part A, we want to find this commission as a function of sales. So we want to find a function C of S. All right. Now this is going to lead us into, since it's different for each one of these values of S here, we're going to talk about what the, basically we have a piecewise function here, okay? So again, remember that S is your sales. So now if your sales are less than 300, then C of S is equal to 20% of your sales. So 0.20 is how we say 20%. So it's 0.20 of S. Now, if S is 300 or more, but less than 400, then it's different. Then your C of S is 60 plus 35% of the sales over 300, right? So it's 0.35 times S minus 300, right? Because it's just on what is over 300, right? So if you have, for example, 350, you went $350, you went $50 over 300, and you could figure that out by just subtracting 300, right? And then finally, if it's 400 or more, so if S is greater than or equal to 400, then it's different. We say this is C of S is equal to 95 plus 0.60 times S minus 400. Right, and of course you could simplify these if you wanted to, which we'll actually do because that will help us. So we can say that C of S is equal to three different things depending on what your S values are. So if S is less than 300, it's 0.20 S. Now, if we simplify this, I'm going to get 60 plus 0.35 S minus 0.35 times 300, which will give you, I'm just going to punch it out in the calculator, 105. So we get that this is minus 105. So if we combine like terms, we're going to get 0.35 S minus 45. And that's if S is between 300 and 400. Okay, and then for this one, we're going to get 95 plus 0.6 S, and then we'll get a minus 240. Right, so then if we combine that, we're going to get a 0.6 S, and then we should get a minus a 145. Right, if I subtract 95 from that, I should get 240. Wait a minute. Does that right? So 240 minus 95. Minus 95. Yeah, 145. I don't know why I'm second guessing that. Okay. And of course, that's for when S is greater than or equal to 400. So that's what's called a piecewise defined function, because for different input values, your function is defined differently. Now for part B, we want to find the commission if the weekly sales are 425. So we want to find C of 425. Now, since this is piecewise, depending on what your input value is, you need to use a different function. So where does the input value of 425 fall? That falls into this last one. So I would need to plug that into the last section here. So 425 minus 145. Okay, so if we do this, if we do 0.6 times a 425, we get 255. And then if we subtract 145 from that, we'll get that this is a 110. All right, so if your sales are 425, the commission that you would get is 110. Okay, now part C, they want you to sketch a graph, and we'll just sort of do a rough sketch because this will be quite a large graph here. Okay, so we know that if we say this is 300 and this is 400, those are sort of our breaking points, right? So if S is less than 300, maybe what's one good thing to do in this is to figure out what the boundary values would be. So if we figure out what C of 300 is for these two, right? We know that in the first one, 0.20 times 300 would be 60, right? And of course, if you plug in 300 into the next one, you're just going to end up with 60 as well, right? Because this part, you can see here that that part would zero out and you'd just be left with the 60. So it looks like wherever 60 is, that's sort of my point here. Right? And then for C of 400, right, if I plug that into here, then we should get a 95 in both cases, it looks like. So let's just save a little bit of time there. Okay, now what's happening here is that in the first section, you're climbing at a rate of 20%. So you have maybe something like this. But in the next part, you're increasing by 35%. So it's a little bit steeper here. And then in the next section, you're increasing by 60%. So you're increasing even more. So that's going to be a little bit more steep. So something like that. All right. So again, in each region, it's defined differently. So that's one thing to keep in mind. Now here, these sort of boundary points were connected. So we didn't have to worry about sort of any jumps or anything, right? But that's one thing that will come into play, I'm assuming, in the next example. Yeah, it looks like it. Okay, now in part A, we have the graph that's defined by x squared if we're between -2 and +2, and by 2x plus 1 if it's between 2 and 5. All right. Now, when we graph this, again, we sort of have two things to worry about, and this one we'll do nice and slow. All right, but if I do x squared, that's for -2 to 2. Right, and if I plug those values in, I'll get 4, 1, 0, 1, and 4. So for that section, I get something like this. Oops, I keep doing that. Don't want an error here. Just something like this. All right. Now for 2x plus 1, my x values are between 2 and 5. But note that 2 is not included, so for that point, I would need an open circle. Right, but if I plug these in, I'm going to get that this is a 5, this is a 7, this is a 9, and this is 11. Right? So now at 2, I'm going to jump from 4 directly to 5 with an open circle there. Right? Because on this graph, my point is 2 comma 4, and on this graph, my point is 2 comma 5. Right? But this is a function, so I can't have overlap. So one of them needs an open circle, right? And of course, this one is going to look something like this. All right. Okay, so that's part A. So let me give myself a little bit more room for part B. So for part B, we have 2x and 5. And this is for -2 to 4. And this is x greater than or equal to 4. Right? Yeah, okay. So I'll do this one a little bit more quickly. So we need from -2 to +4. And since I know that 2x is just going to be a line, I'm just going to plot sort of the endpoints. I'm going to plot -2 and 4. If I plug in a -2, I get a -4. And if I plug in a 4, I'm going to get an 8. Right? So at -2, I have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. And so for -2, -4, that has a closed circle, right? Because of this equal sign, we're including it. And since the 4 doesn't have the equal sign, I still have a point there, but it's an open circle. So I'm going to have something sort of like this. And of course, you can verify that all the points in between would be connected. And this is supposed to be a straight line, but I can't draw very well. So that's what we're going to get. Now for the rest of the graph, when x is greater than or equal to 4, my y value is always the same. My y value is 5, no matter what I plug in. So 1, 2, 3, 4, 5. We're going to have a closed circle here, and it's always going to be 5 no matter what. So there we can put an arrow because it's always for any values greater than 4. It doesn't stop anywhere. All right, so we get something like that. Okay. Now, the next type of graph that we can talk about is a linear function. Well, the next function we can talk about is a linear function, right? So if you have something that looks like or can be written like ax plus b or something times x plus something else, we refer to that as a linear function. And you might have seen this before in the form. Usually we say mx plus b, right? Where m is your slope and b is your y-intercept, right? Now, what does the graph of a linear function look like? Well, creativity of mathematicians is on full display here. And of course, it's a straight line, right? So that's where you get the name linear from. Now, if you have 2 points of a linear function, that's enough to draw the line. You don't need any more than 2 points. So we don't have to draw like 5 points anymore. Right? So in this example, we want to graph each of these lines. So for part A, if I wanted to graph y equals x, or f of x equals x, we can just pick 2 points. So how about 0 and 1? Well, if we plug in 0, we get y is 0. If we plug in 1, we get y is 1. So y equals x. If we plot these 2 points, we're going to have something like this. Right? Well, we know that it's linear because it's 1 times x plus 0, or something times x plus something else. So with 2 points is enough. So this graph looks like this. Okay, in part B, we have that g of x is negative x plus 2. And again, this is linear, so we can get away with 2 points. So if I plot 0 and 1, we'll get negative 0, which is still 0 plus 2 is 2. And negative 1 plus 2 is positive 1. Right? So then we have 0 comma 2 is here. 1 comma 1 is here. So we're going to get something like this. Okay, part C, we have h of x is 2x plus 1. So if we plot our points here, 2 times 0 is 0, plus 1 is 1. If we plug in 1, we get a 2 times 1, which is 2, plus 1 is 3. So then my 2 points are going to be here and here. So that's what my graph there looks like. Okay, and then part D, we have that k of x is equal to negative 3x plus 1 . So again, we can plug in x and y, plug in 0 and 1 and find out what y is. So for 0, we're going to get 1. When we plug in a 1, I'm going to get a negative 3 plus 1, so negative 2. So I'm going to get 2 points, 1 here and 1 here. So when we connect them, we get something like this. All right, so those are a couple of graphing examples. Okay, now if you have a quadratic function, which if you remember our factoring videos is something like ax squared plus bx plus c, all right? Now the graph of this function is called a parabola. And when we say a parabola, we mean something that looks like this or something that looks like this, all right? And of course, we'll spend a little bit more time on this a little later on in the course. We'll do a chapter specifically devoted to quadratic functions, but for now, we'll just use a table of values with a couple points, right? So for part A, we want to graph f of x is 2x squared minus 4x plus 3. Okay, so if we have a table of values here, I can do something like, let's just do our usual negative 2, negative 1, 0, 1, and 2. Okay, now if I plug in a negative 2, I'm going to get 2 times negative 2 squared minus 4 times negative 2 plus 3. So this will give me a 2 times 4 plus 8 plus 3. So we get 8 plus 8 plus 3. So we're going to get a 19 there. Okay, if we plug in negative 1, get a 2 times negative 1 squared minus 4 times negative 1 plus 3. So we're going to get a 2 plus 4 plus 3. So that's going to give us a 9. If I add, if I plug in a 0 there, my x terms go away and I'm just going to be left with 3. If we plug in 1, we get a 2 times 1 squared is still 1. So I'm just going to write that. Minus 4 times 1, which is still 4. So then we're going to get a 2 minus 4 plus 3. So that should give me a positive 1. Okay, and then finally, when we plug in 2, we're going to get that this is a 2 times 4, so an 8, and then minus an 8, and then plus 3. So we get a 3 here. All right, so I'm just going to worry about the negative 1, 0, 1, and 2, since 19 will be way off the page. And even the negative 1 point is pushing it. 4, 5, 6, 7, 8, 9. Okay, so I have negative 1 comma 9, so that's up here. 0 comma 3 would put me here. 1, 1 would put me here. And 2, 3 would put me here. So I'm going to get something like this. Okay, let's do part B. For part B, we have g of x is equal to negative x squared plus 4x minus 5. Okay, so let's go ahead and we'll just plot our usual points again. So x and y, -2, -1, 0, 1, and 2. So if we plug in a -2, we're going to get a -2 squared. Here you got to be careful. Plus 4 times -2 minus 5. So we're going to get a -4 because that -2, once we square it, we'll get a +4, and then we still have the negative out front. And then -8 minus 5. So that's going to give us a -17. Okay, if we plug in a -1, we're going to get a -1 squared plus 4 times -1 minus 5. So we're going to get -1 minus 4 minus 5. So that's -10. If you plug in 0, you can see that you're just going to end up with -5. If you plug in 1, you're going to end up with -1 plus 4 minus 5. So that's going to give us, what, a -2. And when we plug in a 2, we're going to get a -4 plus 8 minus 5. So that's going to give us a -1, it looks like. Right? Now, since all my values are decreasing, I don't have sort of the, and I'll show you what I mean by this real quick. Right? So if I have -2, -1, 0, 1, and 2, I have, at -1, I have -10, which is still like down here. At 0, I have -5, which is here. At 1, I have -2. And at 2, I have -1. So I don't really have the come back around point yet. So let's maybe just plot one more. So if we plot 3, we're going to get -9 plus 12 minus 5. So then that's going to give us a -2, and we do see we do start to come back down. So if we plot one more point, we start to get the shape that we want. So we get something that looks like this. We'll pretend that I can draw. All right, so something like that. Okay, so to finish off this section, we'll just make a remark that if you have a polynomial, which we discussed in a previous chapter, if you have a polynomial that has one variable, that's always a function. Right? So of course, linear and quadratics are just examples of polynomials. And of course, we saw that they were functions, right? Any line that you have, unless it's a vertical line, of course. So any line that's non-vertical and any quadratic or any parabola is always a function. Okay. Now, of course, higher degree polynomials, so if you have a third power, fourth power, 17th power, they're going to be, of course, more complex, but they're always nice and smooth curves. All right, so that's sort of what we'll finish off with in this section. All right, so that concludes this video on graphs of functions. I hope you enjoyed, and I will see you next time.